we look into whatever we studied in Gauss law. Then define divergence and then use it to talk about Gauss Divergence Theorem. And finally, we will look into very, very important applications of Gauss law to determine electric field intensity. Wherever there is a kind of symmetry in the field. Please check it now. We stated Gauss law for the flux density, displacement flux density. D bar. It's a vector, having the unit of Coulomb per meter squared. Related to electric field intensity through the equation. At any point, if you know D bar, electric field intensity is D bar by the permittivity of the medium in which we are discussing the field. This is definitely not a measurable quantity, imaginary quantity just given. Because we cannot see it. Given this, we saw that closed surface integral d bar dot ds bar. Word statement is important. We discussed it already. So I will not do it today. It is mathematics. Closed surface integral of d bar dot ds bar is essentially the total outward normal flux through the given closed surface. At each and every point on this closed surface, we should select a ds and then talk what is ds bar by giving the normal to that particular differential surface. At that point, we have d bar take the normal component of it by taking d bar dot an, outward normal is an, integrated with respect to ds. Total outward normal flux through any closed surface is equal to the charge q, which is net charge enclosed by the closed surface. Integral d bar dot ds bar equal to net charge enclosed by the closed surface is a universal statement. This is universal. It's a sweeping statement, unconditional. This charge can be one point charge, many point charges, one line charge, many line charges, one surface or many surface charges, one volume charge or many volume charges inside. can be discrete, continuous, unconditional it is. For all types of charge distribution over the volume enclosed by the closed surface under consideration in the integral. Q. This is what is the statement in fields for us. Next, using this, please check. Check whether this statement is clear or not. Given d bar at any point, provided, today I am talking about this, provided it is continuous everywhere. Explanation follows. I have given d bar at any point in the given region, provided it is continuous everywhere. We can determine the charge density at every point. Yesterday, we saw that it is divergence. We proved it. But for the sake of mathematics, I need not worry about the proof. I need the formula. We derived the volume charge density to be dou by dou x of dx x component of the flux density plus dou by dou y of dy. Coulomb per meter squared is flux density, dou by dou x is meter cubed. Dou by dou x of dx plus dou by dou y of dy plus dou by dou z of dz means what? Partial derivatives of the respective components. X component with respect to x, y component with respect to y, z component with respect to z. And we know very well, that in mathematics, only continuous functions are differentiable. Only continuous functions are differentiable. I want you to know this now. Listen carefully. There are cases where the flux density or electric field intensity both are same or discontinuous. Please check it. Let us suppose I have a point charge here. I will just move along x direction. Same thing will happen for y direction, everything. Let us suppose this is x. The expression for a point charge q, the expression for the flux density at any point which is at a distance d from q is seen to be q by 4 pi d squared. Q by 4 pi d squared at d tending to 0 is what? infinity. It decreases like this. To the right, if it is positive, to the left, it will be negative. You agree with this? Yes or no? Along x-axis, positive charge only, field lines will go out from the positive charge. On positive x-axis, keeping the charge at origin, along positive x-axis, it is along positive x only. On negative x-axis, it is along negative x, means what? Its direction is opposite. And at d tending to 0, 4 q by 4 pi d squared is infinity in magnitude. To the left, it will be like this. I want you to know this because in critical examinations, at higher level examinations, they can always bring this as a point in the question. Same thing will happen in whichever the direction you go through the point charge. The field intensity will increase to the infinity because at the distance tending to 0. Again, on the other side of the charge, the polarity will change. Minus infinity, if it is plus infinity on one side, minus infinity on the other side, and then again decreases to 0 when the distance becomes equal to infinity. Is the field intensity or flux density created by a point charge continuous? There is discontinuity, right? Infinite discontinuity is there. 0 minus is minus infinity. 0 plus is plus infinity. It is not differentiable at k is equal to 0. So, by using this flux density, I cannot determine the point charge q there. But in this region, for all x greater than 0, if it is the region, it is continuous in this region, because of which it is differentiable there. It is differentiable to the left also, but it is not differentiable at x is equal to 0. It is not differentiable at the charge. Please check it. We are going into the specifics of it. Then we took the line charge, we determined the field. Rho L by 2 pi epsilon r. Here also, r tending to 0, it is infinity. On the right, r tending to 0 on the left, definitely the direction has changed. Minus infinity, because r is there in the denominator. In this case also, if at all charge is there in that region, only line charge is there. In the other region, no charge is there, because of which the field distribution is this. When I say that this is the field distribution of point charge, no other charge is there, only one charge is there, creating the entire field. This is line charge. This is actually infinite discontinuity. If a function is discontinuous at a point, at that point it is not differentiable. Correct? Next. One wonderful thing that we have to see, because that itself is boundary conditions for us, which are extremely important for a communication engineer, at least for the sake of talking about reflection of electromagnetic waves. We saw that if this is a surface charge, in the case of surface charge, we saw rho s by 2 is the flux density, rho s by 2 epsilon is the electric field intensity. It is not dependent on the distance if it is infinite surface charge. Infinite line charge, infinite surface charge. In that particular case, if to the right of it, if it is plus rho s by 2 to the right, rho s by 2 to the right, rho s by 2 will be there on the other side, because of which there is left also, right? Everywhere it is same. I told you that it is uniform on each side of this particular plane. Rho s by 2, rho s by 2 are the flux densities. Here we have finite discontinuity of size rho s. Check it. Discontinuity is what? The amount of step change that is happening at that particular point is size of discontinuity. It's actually minus rho s by 2 because it is there to the left. This is rho s by 2 changes rho s. If you have studied boundary conditions, this is what it says. The flux density at any point on the boundary of two media is discontinuous by the amount equal to the surface charge density on the boundary. Straight result it is. If there is no surface charge, there will be no discontinuity. It will be same either side, on either side. Because of the charge, somewhere field is there. Continuous if there is no surface charge. Basically, the statement is the normal component of the flux density at any point on the boundary between two media is discontinuous by the amount equal to the surface charge density on the boundary. If there is no surface charge density, there is zero discontinuity. Zero discontinuity says it is continuous. I cannot determine, please remember, using Gauss law, using d bar at each and every point, I cannot determine the charge of a point charge density of a line charge of infinite length, or charge density of a surface charge of infinite, because on the point where the charge is actually there, it is discontinuous, because of which I cannot differentiate and say this is the amount. Wherever it is continuous, there is no change here, because of which there is no charge here. Listen carefully. When you find out the divergence at this particular point, I will show it later. When I find out the divergence in this particular region, in the field created by a line charge, point charge, a surface charge, away from the source, divergence is zero. There is field, but zero divergence. It will have zero divergence. How did we determine? How to determine the volume charge density? Volume charge density can be determined if it is uniformly distributed. Carefully see the statement. Given d bar at any point, provided it is continuous everywhere, we can determine the charge density at every point. Now, how to modify this? Given d bar at every point in a region, wherever it is continuous and differentiable. Hey, when this, are all continuous functions differentiable?
No.
Who is telling that? Abhishek? Example?
Mod x.
any sudden change in the slope, they are not differentiable. Differentiable if slope also is continuous. Correct? Continuous and differentiable. Anyway, here normally it will be differentiable if it is continuous. But we should be proper in giving the statements. If d bar at every point in a region wherever given d bar, wherever it is continuous and differentiable, we can determine the volume charge density rho v using what? Hey, what is rho v? We know very well. This is what I was telling. We have huge advantage in understanding this. Rho v is what? We know rho v at any point in any charged region to be defined as limit delta v tending to 0. Differential volume delta q by delta v. Correct? Delta v tending to 0, delta q by delta v is rho v. The delta q is present in the differential volume. Definitely any differential volume, standard differential volume in any coordinate system is inside a closed surface, right? Imaginary closed surface. So we apply this is equal to what? Limit delta v tending to 0. Charge inside is what? Closed surface enclosing the volume. D bar dot ds bar, we evaluated it, divided by delta v. This by notation is given as del bar dot d bar. In fact, listen carefully. In vector calculus, mathematics part, they say for any vector field, that means any field described by a vector quantity at each and every point, integral v bar dot ds bar over a closed surface, it can be any vector, is equal to volume integral of del bar dot v bar dv. And they just define. Read all mathematics textbooks possible. They just define, even electromagnetics textbooks. Say delta v, del bar dot v bar is limit delta v tending to 0, integral over a closed surface, v bar dot ds bar divided by delta v. That v bar is vector, some other vector field. Delta v is volume. But we know very well that rho v is this. And if rho v is the volume charge density at every point, inside the closed surface. Correct? That is what is important for me. The charge is not discrete. The charge is not set of point charges here. Charge is not set of line charges or surface charges. Or it is not discrete. I say everywhere it is there, rho v. If rho v is the volume charge density at every point, it is continuous distribution inside the closed surface. Integral over the closed surface d bar dot ds bar equal to volume integral of Q, right? Rho v dv. This is actually Q present inside the closed volume. Here, please remember, there is no Q in mathematics. Nobody talks about this charge in mathematics when you talk about V bar. Not even to explain for an example. Charge is not given to you. Some vector field. For any vector field, this is actually what? Integral. Now we know d bar dot ds bar is equal to volume integral of del bar dot d bar scalar volume integral of scalar. Because rho v is del bar dot d bar at any point. I'm sure you are going to see the possible wonderful applications of Gauss law today. See now, this is what we are supposed to know. Divergence. Divergence is always of a vector field. Vector. I can talk about vector field also. But del bar dot d bar. Divergence of a vector field is, it is a scalar. Because it is dot product. That scalar is, if that vector field happens to be flux density, that scalar is volume charge density. Correct? I'm talking about vector field. Del bar dot v bar is a divergence. We derived the expression for del bar dot v bar in Cartesian coordinate systems in which we did not actually do a lot of approximations. Whenever we try to derive the same thing in curvilinear coordinate systems, essentially spherical and cylindrical coordinate systems, I'll tell you, the derivation becomes tedious because of the products of differentials in which so many are to be discarded. And we have to remember what is to be discarded, because of which I feel sincerely, maybe very few places only I normally give the formula and ask you to remember this. This is one place. As far as possible, we derive. Because the ability to derive is our strength actually, ultimately. Del bar dot d bar in any coordinate system, please concentrate because you know this and use it. Know how to use it. 1 by H1, H2, H3 within brackets. Dou by dou u is the first coordinate. V bar is the vector I took of H2, H3, VU, U component. like no x component or rho component or r component in different coordinates is the first thing. Plus next covariant variable is dou v. U, v, w are the coordinates like x, y, z, rho, phi, z, x, y, yeah, x, y, z, rho, phi, z, and r, theta, phi. H1, H3 times VV for any vector field V bar. Plus dou by dou W of H1, H2, VW. Where I'll just speak about it. We saw that in Cartesian coordinate system, dl bar is equal to yeah, dx ax plus dy ay plus dz az. You know this. Where we vary x by dx, dx only will be the component because they are all independent. Y by dy, keeping other two constant, y only will change. This is first one. Coefficient to dx is 1, h1. This is also 1, h2. This is also 1, h3. I'm rounding them off in order. In cylindrical coordinate system, we saw that it is d rho a rho. Coefficient is 1. Plus, I will keep rho as constant at any rho phi z. Vary phi. What is that component? Rho d phi. Rho d phi a phi. This is the coefficient coming out. It's not 1. In order h1, h2, h3 plus 1 times dz az. I will say h1 is this, h2 is the second coefficient, h3 in different coordinate systems. In spherical coordinate system, 1 dr ar plus r d theta a theta on the cone plus r sin theta d phi a phi. 1 r sin theta or h1, h2, h3. Check it. Mathematics people will never come to these things, but it's better that you know about h1, h2, h3, at least for the sake of antennas and wave propagation. Antennas, no? We talk about curl of in spherical coordinate systems. There also we define everything with respect to h1, h2, h3. That way, del Cartesian cylindrical spherical coordinate system. Please check it. Now del bar dot v bar for any vector field in different coordinate systems is what? All h1, h2, h3 all are ones because of which UVW or XYZ. Dou by dou x of Vx. This is what we derived yesterday. Dou by dou y of Vy plus dou by dou z of Vz. Z component. Next, dou by dou rho of V rho plus, sorry. What is 1 by H1 H2 H3? 1 by rho. Please check it. 1 by rho outside. Dou by dou rho of H1 H3. Sorry, H2 H3. Correctly? H2 H3 is what? Rho. Rho component of V. This rho inside and outside, they will not get cancelled out, right? You have to differentiate it by using UV and then divide it by rho. Plus 1 into rho into 1, I wrote as 1 into rho into 1. Dou by dou rho. H2 H3 V rho. Next, dou by dou phi of H1 H3 are 1 ones, right? Because of which it is straight away V phi. Plus dou by dou z of H1 H2 is what? Same. Dou by dou z of rho Vz. 1 by rho totally. At any point, rho phi z. Followed by in spherical coordinate system. Please keep interacting. H1 1, H2 R, H3 R sin theta 1 by R squared sin theta within brackets dou by dou R of H1 H3 is R sin theta times VR plus dou by dou theta of
Sir, it is H2 H3.
R squared sin theta, right?
Yes.
This R squared sin theta for 1. Dou by dou theta of, now it is
R sin.
R sin theta V theta plus dou by dou phi of H1 H2 is just R. R V phi. Complete thing divided by R squared sin theta. Check it out. And I wrote it following this universal expression for the divergence of a vector field. Now, what is Gauss divergence theorem? In mathematics, given the vector field V bar, given the vector field V bar and its divergence del bar dot V bar, basically defined at in mathematics limit delta V tending to 0 closed surface integral of V bar dot ds bar divided by delta V. That we know from the charge density and its divergence del bar dot knowing given. Its divergence is, we'll put its divergence is del bar dot V bar and Gauss divergence theorem. Closed surface integral, so many double integrals. 6 in each coordinate system. V bar dot ds bar is equal to closed surface integral. V bar dot ds bar is equal to volume integral over the volume enclosed by the closed surface. Del bar dot V bar volume integral of scalar quantity is Gauss divergence theorem. Instead of evaluating V bar dot ds bar over 6 different phases and getting that particular value, if you can differentiate V bar as per the formula given by del bar dot V bar, one triple integral will give you the same answer. There are so many cases in which it gives us the mathematical advantage.